Hello grade 9 students, this is Mr. Muhammad Khurfan with you. Today's lesson inshallah will be about spherical mirrors. We have two types of spherical mirrors, concave mirror and convex mirror. In order to differentiate between these two types, concave mirror is silvered inside, curved inside, while the convex mirror is silvered outside or curved outside. In this lesson, we're gonna see 5 cases that are related to concave mirror and only one case that's related to convex mirror. Before starting with the cases, we will start a general definition about concave mirror. Now, as we see here, this line is the principal axis. Principal axis, as a definition, is an imaginary line that's perpendicular to the mirror. On this line, we have 3 points lying on it, M, F, and C. Point M is the point of intersection between the mirror and the principal axis. Point F represents the focal point. Focal point, it means something, and a very important thing, that the line, the reflected ray from the mirror, gonna pass through F. First of all, let's take this one, which is the incident ray. Let's say we have a coming incident ray. This incident ray, which is parallel to the principal axis. Any light ray, if it comes parallel to the principal axis and hits the mirror, so its reflection will be focused, its reflection will pass through point F. That's why we call this point F the focal point. Point C. Point C is the center of curvature of the spherical mirror. We are saying spherical mirror. It means that this concave mirror is part of a complete sphere. Sphere, it means it has what? A center, which is C. But we are taking only one part of the sphere, only this arc, which is the arc that's related to the spherical mirror, which is the concave mirror. The distance from point C to the mirror is the radius R. In spheres, in math, the distance from the center to the circle represents the radius. Also here the same concept, the distance from point C to point M represents the radius. As we see, F is halfway this distance between M and C. That's why F is considered as radius over 2. F is half the radius. Now, let's take another light ray. Another light ray that's coming also parallel to the principal axis. Since the light ray is parallel to the principal axis and hitting the mirror, so its reflection also will be focused and it will pass through F. So, as a note, any light ray, if it comes parallel to the principal axis and hits the mirror, so its reflection will pass through point F. That's why we call this mirror another name, converging mirror. It means the reflected rays converge, meets, intersects at one point. So the reflected rays intersect at one point. So far so good. And these are the definitions for each point. As we see here, point F is the focal length. There's a difference between the focal point and focal length. Focal point is the point where the reflected rays intersect and meet together, while point F represents small f, which is this one, is the distance between capital F and M, and its name is focal length, is the distance between F and the mirror. So far so good. Now we're gonna start with the 5 cases that are related to concave mirror. Everything depends on the position of the placed object itself. First of all, here we're gonna take these points M, F, and C. First of all, I will place the object between F and M, between point F and point M. Here, the point, let's say A, B. As usual, we're gonna take two light rays from this object. First light ray will be parallel to the principal axis. So first light ray will be parallel to the principal axis. And as we said, any light ray, if it's parallel to the principal axis, so its reflection will be or will pass through point F. Now the second incident ray. The second incident ray, it will be perpendicular to the mirror. Any light ray, if it comes perpendicular to the mirror, so any incident ray, if it comes perpendicular to the mirror, so it will reflect along the same path. So its reflection will pass through the center of curvature. So till now, we have these two lines. We have, first of all, the incident ray parallel to the principal axis, as we see here. Since it's parallel to the principal axis and it's hitting the mirror, so its reflection will pass through point F. The second incident ray from also point B, perpendicular to the mirror. Any light ray, if it's perpendicular to the mirror, so its reflection will pass through the center of curvature C. And the reflection here is, as we see here, along the same path. We know that the image simply, it's the intersection of the reflected rays. On the left side, the reflected rays, they didn't intersect. So we will check if they intersect on the right side, which is behind the mirror, in front of the mirror, in this place. Now, in order to check, simply we're gonna elongate the reflected rays. So here we have, this is the first reflected ray, which is going to the left. Now I will elongate it back in order to check if it's gonna meet the other reflected ray. And here we have the second reflected ray. Also, we're gonna elongate it back, which is this one, the dotted line behind the mirror. So the point of intersection here between the two reflected rays forms the image. The point of intersection forms the image where we have A prime and B prime. A prime is the image of point A, while B prime is the image of point B. So A prime is the image of A, B prime is the image of B. So that's why A prime, B prime, all of this image, or it's the image of AB. Now, each case has characteristics, as we see here. These are the characteristics of the first case. First of all, the type of the image is virtual. Virtual since it's behind the mirror. So, since it's behind or inside the mirror, so the type is virtual. Virtual, it means now the distance from the image to the mirror, it should be negative. This is xi. Xi is the distance from the mirror to the image. F is the distance between the focal point and the mirror. Xo is the distance between the object and the mirror. Xi in this case will be less than 0. It means negative, since it's inside the mirror. Xo, which is the distance between the object and the mirror, it will be positive, greater than 0. That's why the type is virtual, since xi is negative, the object is inside the mirror. Now, the direction of the image, the direction is upright. Upright, same as the object. So, since it's upright, same as the object, in this case, HO, it's positive, then it represents the height of the object, and HI is positive also, since it represents the height of the image. Since it is upright, so it represents the height of the image, it will be positive. So now, any image, if it is virtual, so always it will be upright. It's impossible to see virtual image with inverted or upside down image that we're gonna see it later on. Size. The size, as noticed here, is enlarged. The size now is enlarged. It's taller than the object. The size of the image is taller than the object. Number 4, the position. Position of the image itself, it's deeper inside the mirror. So once you have a virtual image, so of course it will be inside the mirror. This is the first case number 1. Now we're gonna move on to case number 2. Here we have point M, point F, and point C. Of course, these points are lying on the principal axis. Now, I will place the object at point F. In the previous case, we placed the object between F and M. In this case, we will place the object at point F exactly. Also, we're gonna take 2 light rays. Let's say in this object it's AB. This object could be anything. Of course, it could be a certain car, it could be a certain bag, and it could be you. So now we have AB, the object. As usual, we're gonna take 2 light rays from this object. This is the first one, which is parallel to the principal axis. And as we said, any light ray, if it is parallel to the principal axis, of course I mean the incident ray, if it is parallel to the principal axis, so its reflection will pass through point F. This is the first light ray. Now, the second light ray. The second light ray that will be produced from point B is perpendicular to the mirror, as we see here. Also, any light ray, if it is perpendicular to the mirror, so its reflection will pass through point C, which is the center of curvature. On the left side, there is no intersection for the reflected rays, as we see here. They didn't intersect. So we need to check on the right side by elongating the reflected rays, back. So by elongating the reflected rays to the right, also here we can notice that the reflected rays also they didn't intersect. This means that the reflected rays will intersect at infinity. So in this case, we cannot see any image. So there is no image in this case, which is case 2. Now, the distance from the object to the mirror is XO, and the distance from the focal point here till the mirror is F, as we see, which is focal length. Case number 3. Now, we will place the object between C and F. We will place the object between C and F. We can notice that everything depends on the place of the object, on the position of the object. Now the position is between C and F. This object also, I will name it AB. 2 reflected rays will be produced from this object. So the first light ray, as usual, parallel to the principal axis. This incident ray, since it's parallel to the principal axis and it's hitting the mirror, so its reflection will be through point F. Now the second light ray. Of course, here you may think, and I will take the light ray also perpendicular to the mirror. Now, I will change a little bit the strategy. The light ray now, it will pass through point F, the incident ray. Let's check what will happen. So it's another rule. Any light ray, if it passes through point F, so any light ray, which is the incident one of course, if it passes through point F and hits the mirror, so its reflection will be parallel to the principal axis as we see here. It's completely opposite to what? Opposite to the first case when we took the incident ray parallel to the principal axis. So here the incident ray is passing through point F and hitting the mirror, so its reflection will be parallel to the principal axis. Its reflection will be parallel to the principal axis. As we see here, these two reflected rays intersect at this point. So the point of intersection of the two reflected rays forms the image, which is this one. This is the image of the object A prime, B prime, where A prime is the image of A, B prime is the image of B. Now, as we see here, the image is real image. The nature of the image is real. Why real? Since it's in front of the mirror, it's in this part in front of the mirror. It's not behind the mirror anymore, it's in front of the mirror. So in this case, the image is said to be real. Also, the image here, as we see, it's inverted. It's not upright anymore. Always, once you have a real image, this means that this image will be inverted. It's impossible to be upright and real at the same time. The size of the image. The size of the image is enlarged. It's much more than AB. It's taller than AB. The position, it's beyond C. The position of the image is beyond C. Now, xi, as usual, it's the distance between the image and the mirror. Xi in this case is said to be positive. Positive since it's inside the mirror. Or in front of the mirror. Point F, here is the focal length, where is the distance from point F to point M. As we see here, so the reflected rays, any reflected ray, again, like as a review, if the incident ray is parallel to the principal axis, so the reflected ray will pass through F. But this one, which is the incident ray, it passed through point F, so its reflection, of course, will not pass through point F. It will be parallel to the principal axis. The reason, because the incident ray is not parallel to the principal axis. Only one case, the reflected rays will be converged, will meet at point F when they are parallel, when the incident ray parallel to the principal axis. So far, so good. So XO now is the distance between object and the mirror. Also, it's positive. XO, guys, it's impossible to be negative. Always, it's in front of the mirror. Logically, it's impossible to be inside the mirror. Now, here we have the characteristics for case 3. The type is real, as we see. XO and XI, both of them are positive. XI positive since it's in front of the mirror. The direction is inverted. As we see, it's upside down. The height of the object is positive, while the height of the image is negative. The size is enlarged. As we see here, HI is much more than HO, greater than HO. Here an absolute value, since if we want to compare, for example, height as a magnitude, as a real values, so we take only the positive values. So that's why the absolute value of HI greater than HO. Position, now it's beyond C. Beyond C. There's an important note that point C also, it could be named 2F. So it's C or 2F. Sometimes it's C, sometimes it's 2F. It depends on the reference or on the using or on the book used one. Now, case number 4. Concave mirror here. The image, it's important, now will be produced, but the condition is the object now is placed where? At point C, exactly, at the center of curvature. So far so good. A, B. 2 light rays will be produced from this object as usual. The first one parallel to the principal axis, which is this one. As we said, any light ray, if it's parallel to the principal axis, so it's gonna converge. Converge, it means what? It means it's gonna meet another reflected ray. If it comes parallel to the principal axis, the incident ray, so its reflection also gonna converge and meet the first reflected ray. This is the meaning of converge, or focused at point F. Now, the second light ray also it's gonna pass through point F and it's gonna hit the mirror. As we said, any light ray, if it passes through point F and hits the mirror, so its reflection will be parallel to the principal axis. Parallel to the principal axis. The two light rays intersect at this point, so it's the point of intersection of the reflected rays. It means it's the image. This means that the image will be set at point C exactly. So far so good. So till now the image is, as we see, since it's in front of the mirror, it's real. The type or the nature of the image is real. Number two, its direction is inverted. Since it's real, so it will be inverted. Again, it's impossible to be real and upright. Real and inverted. Inverted, it means now in this case HI will be negative. XI, since it's real, so it will be positive. XO, always positive, as we said. HO, in this case positive, since it's upright, HO, but the image now is negative, which is HI, since it's inverted. The size of the image, same size exactly as it's noticed here, same size exactly. So HI as an absolute value, if you want to compare, for example, the heights, so we take in this case the same or positive values. Number four, the position also it's exactly at point C, which is the center of curvature. So far so good. So these are the characteristics, as we said, that are related to case number 4. Case number 5. Now we will place the object beyond C, this object A, B. Two reflected rays as usual will be produced from point B. This is the first reflected ray, as usual, parallel to the principal axis. So its reflection will pass through point F, will be focused at point F, which is the focal point. Now the second light ray also, it will pass through point F and gonna hit the mirror. So in this case, the reflection will be parallel to the principal axis. The reflected ray is gonna meet on this point. This point is the point of intersection of the reflected rays, which it represents the image, which is this one. So this is A prime, and here we have B prime. In case number 4 here, A prime, it's here, and B prime, it's here. Where A prime is the image of A, B prime is the image of B at the same point. Okay? So till now, here we have B prime is the image of B, and A prime is the image of point A. Since the image now is in front of the mirror, so it's set to be real, greater than 0. The distance from the object till the mirror is also positive. Now, the height, since it's inverted, it means the height it will be negative. And the object, since it's upright, so the height will be positive. The type of the image, or the real of the or the nature of the image is real. Both of them here, xi and xo, are positive. The direction now is inverted. It's important. Real inverted. So HI, it will be negative. The size is reduced, as we see here. The size is reduced. It's smaller than, so the image now is smaller than the object. The position is between F and C. This is point F, and here we have point C, and the image in between. So these are the 5 cases that are related to concave mirror. Now convex mirror, which is the only case that's related to convex mirror. We're gonna see here a very important thing. No, point F is inside the mirror. Point F, it's inside the mirror. Also point C. Convex mirror, also it's a spherical mirror. If you want to complete, for example, this sphere or this convex mirror, you will get a sphere with a center C. The distance between the mirror, which is this one, point M, till you reach the center is a radius. Also F here is half the distance between M and C. So it's half radius. Only in this case, the radius or the focal point and the distance between the focal point and the mirror will be in negative, as we're gonna see later on. So also this one, the convex mirror, is a spherical mirror with a radius C. So far so good. Now here we have the object A, B. It doesn't matter where we put the object in convex mirror. If, for example, if we put it here, or here, or at this position, or at this position, or at this position, it doesn't matter, since the focal point and the center are inside the mirror, not outside. So far so good. Now we have A, B. As usual, we're gonna take 2 light rays. 2 light rays from the object. This is the first light ray, which is parallel to the principal axis. Now it's parallel to the principal axis, and the focal point is inside the mirror. Look what will happen. Now, we know that any light ray, if it's parallel to the principal axis, so its reflection will pass through point F. But in this case, this incident ray cannot penetrate inside the mirror. So the incident ray cannot continue and cannot penetrate inside the mirror. So it will not reach point F. So the reflection of this incident ray will be in this form. In this form. Why in this form? Because if we elongate the reflected ray, it will pass through point F. Again, this step, which is a very important step. Any light ray, if it's parallel to the principal axis, so it should pass through point F. In this case, the light ray cannot penetrate inside, so its reflection will be in this form. Why in this form? It appears, it looks like it's passing through point F when you elongate the reflected ray. That's why it will be in this form. Now, the second light ray. The second light ray, in the previous 3 cases, in the last 3 cases, we took that the second incident ray was passing through point F. The second incident ray was passing through point F. Also here we're gonna do the same process. Since point F is inside the mirror, so the incident ray, it's gonna move toward F, only toward F, until it reaches the mirror. Once it reaches the mirror, this incident ray will not penetrate through the mirror. It cannot penetrate through the mirror, so it will be reflected in a one way. Since the incident ray, as we said, this one, since this incident ray, its destination was to F, so its reflection will be parallel to the principal axis. So the reflected ray will be parallel to the principal axis. The image is the intersection between the reflected rays. Here we have the first reflected ray, which is this one. We elongated the first reflected ray at the beginning. Now we need to elongate the second reflected ray. Why? Since the reflected rays, they will not intersect on the left side. They will not intersect on the left side. So we're gonna check if they will intersect on the right side by elongating the second reflected ray. So this one is the second reflected ray. So by elongating the second reflected ray, these two rays gonna meet at this point, which is a little bit to the right. No problem, it will be here. So it will intersect at this point, which is A prime, B prime, A prime, B prime. A prime is the image of A, B prime is the image of B. So A prime, B prime is the image of the object A, B. As we can see here, the image is virtual image since it's behind the mirror, inside the mirror, so it's virtual image. Number two, the image is upright. The image is upright, the same direction as the object, also upright. The size of the image is reduced, it's smaller than AB, and it's between point M and F. Its size, its position between M and F. Here we have the characteristics. So for every convex mirror, in each case, once you have a convex mirror, always you'll have these characteristics, and always convex mirror gonna produce a virtual image, gonna produce upright and reduced image at the same time. And in this case, it doesn't depend on the position of the object at all. Always you will get this shape and this image. So far so good. Now the focal length. The focal length in this case, it's not positive anymore. The focal length, it's negative. Why? Since the focal point, it's inside the mirror. So the focal length in the case when we have a concave mirror, it will be positive. Once we have a convex mirror, so the focal length will be negative, will be less than 0. So capital F equal negative R over 2 instead of R over 2. So in concave mirror, the focal length, it will be positive R over 2. Since the concave mirror, the focal point is in front of the mirror, it's in front of the mirror, while here in this case, in the convex mirror, as we see, F, it's inside the mirror. That's why it will be negative. Xi, as usual, negative, since it's inside the mirror. Hi, also negative. In this case, Hi, it will be positive. Be careful for this point, since it's upright. Since it is upright, same direction as the object, as the height of the object. So it's upright. In this case, it's positive, and the position is between M and F. So far so good. So this is the convex mirror. Now the equation. Here we have a very important equation, and it's an easy equation in order to find, for example, the focal length here. Simply, in order to find the focal length, you will be given xi and xo. Once you have xi and xo, so it's easy now to find f. It's easy to find f. Sometimes f will be given, xo will be given, and you need to find xi. Always you have two givens, two knowns, and one unknown. So far so good. So this is a very important formula, a very important rule in optics in order to find one of these values, in a condition, of course, the other two terms will be given, where point F stands for the focal length, XO stands for the object distance away from the mirror, image or XI is the image distance to the mirror. Now, here you have a very important note, which is this one. If the distance is negative, the image is behind the mirror. In the question, sometimes we may give you XI in the given, it could be positive, but we could mention, it's behind the mirror. So during substitution, during calculations, XI, it will be negative and not positive. So far so good. This is the equation. And here we have another equation. This equation is related to what? To the magnification. Magnification, it means simply, magnification, it's a constant that allows us to know if the image is magnified or minimized. So magnification, simply, it's a constant. As a definition, it's a constant that allows us to know if the image is maximized, which is enlarged, or minimized. M stands for the magnification. It's unitless. HI stands for the height of the image. HO stands for the object's height. XI stands for the distance between the image and the mirror, where XO stands for the distance between the object and the mirror. Now, you could ask yourself a question. Which one are we going to use? M equal HI over HO, M equal negative XI over XO, or HI over HO equal negative XI over XO? Everything, guys, depends on the given itself. يعني, sometimes if you have given HI and HO, and you need to find the magnification, let's say this one is given and this one is given, and you need to find the magnification. In this case, simply we're going to use M equal HI over HO. Now, if XI and XO were given, and you need to find M, so we're going to use M equal negative XI over XO. Sometimes M, it will not be given at all, and we may give you this one, which is HI, and we may give you HI, we may give you XI, HI, HO, and you need to find what? XO. So you will use HI over HO equal negative XI over XO. Only the right part. So everything depends on the chosen given. That's why the given is so important. So far, so good. Here we have, yes, the magnification. M stands for magnification. HI is the height's image. Object's height, which is HO. Meters, or sometimes could be in centimeters, also depends on the given. Now, sign conventions. When XO is positive or negative, when XI is negative or positive, when F is positive or negative, when M is positive or negative. First of all, we're going to start with XO. XO, simply, it's positive when the object is in front of the mirror. Once the object is in front of the mirror, so XO, it will be positive. Negative, it's impossible. The object cannot be in negative. Simply, you cannot stand inside the mirror, you cannot stand behind the mirror in order to see your image. Simply, logically, you will stand in front of the mirror. You will stand in front of the mirror. That's why XO positive. The image location XI. XI is positive if the image is in front of the mirror. If the image finally, as we saw in cases 3, 4, and 5 in the concave mirror, the image was in front of the mirror, so in this case it will be positive. Negative if the image is behind the mirror. Simply, if the image is behind the mirror, as we saw in case number 1, and that's that one that's related to the convex mirror, so xi, it will be in this case less than 0, negative. So the focal length, so it's positive in concave mirror and it's negative in a convex mirror. Once you know that the mirror is concave, so focal length will be positive, and if the mirror is convex, so the mirror or the focal length is said to be negative. Magnification, if the image simply is upright or virtual image, once you have a virtual image which is opposite to real and upright or upright image actually, so the magnification here will be positive. On the other hand, if the image is inverted or real image, so magnification in this case it will be negative. Simply also also here, if we look on the magnification, let's say the magnification is negative 3. Negative, since it's a negative sign, we can know the type of the image. Since it's the magnification, if it was given negative 3, so negative, it means the image is real image and inverted at the same time. Here we have some notes that are related to the magnification. Always, if the absolute value of m is greater than 1, implies that this means that the image is enlarged, which is what? Magnified. So the image will be enlarged or magnified. If the second point, if the absolute value of point m, of the magnification m, symbol m, is less than 1, implies that in this case the image will be reduced, minimized. If m equals to 1, be careful to this one. If m equals to 1, this means that it will be a plane mirror, as you took in lesson 17.1 about plane mirrors. Now, spherical aberration. Actually, and in reality, it was noticed that the spherical mirrors actually are not suitable in order to produce a certain image and in order to see the image clearly. We faced a problem in spherical mirrors, which is what? The spherical aberration. This problem, it's because the light rays, or actually the reflected rays that were close to the principal axis, so the reflection passes through F. The reflection actually will pass through F. But the reflected rays that are close to the edges, they are not converging and they are not reflecting at point F. They are reflecting at other different points. And once you reach more and more the edges, also the reflected rays will not pass through point F. So this problem, it's called, this one is a defect actually, it's called spherical aberration. The image in this case will not be clear at all. The image in this case appears to be what? Fuzzy or blurry image. The image, it will not be clear at all. Since here we have this problem, this defect, in order to fix this problem, to fix this defect, we use, instead of spherical mirrors, we use parabolic mirrors. So this one, parabolic mirrors, it means the mirror here in this case, it's more elliptical shape. It's more elliptical shape. So by using parabolic mirrors, now wherever you put or wherever you direct the incident rays, the reflected rays will meet at one and only one point, which is F. It's completely different than this one here. So on the left side, the spherical mirrors, the reflected rays that are close to the principal axis, okay, they converge at point F, but the reflected rays that are close to the edges here and here, they are not converging at point F since the type of the mirror is spherical. This problem, this defect is called spherical aberration. In order to solve this problem, we're going to use a parabolic mirror instead of spherical one. So far, so good. Of course, in this case, the image will be clear. Now, examples about this lesson. First of all, sample problem 1. A concave shaving mirror has a focal length of 33 centimeters. As we said, centimeters depends on the given. Calculate the image position of a, here you have, for example, enter a colonia bottle placed in front of the mirror, at a distance of 93 centimeters. Everything, guys, everything here depends on the given. And the most important thing is the given. In order to solve this problem, simply we're going to use this formula, this relation, 1 over F equal 1 over XO plus 1 over XI. Here XO is given, simply substitute XO and substitute F, replace F here, but now you can solve it, of course, by using the shift solve method or mathematically. Let's say we are solving this one mathematically. Now we need to find we need to find Xi. Simply now reorder this equation, redistributed. 1 over Xi here equal 1 over F minus 1 over XO, since we need to find Xi. So equals 1 over 0.33, which is the focal length. Here we substituted the focal length, minus 1 over 0.93 meters. Look, here we converted to meters. So equal 1.955. Now, this is what the tricky step. Guys, we are not finished yet. We are not done yet. We need to find Xi, not 1 over Xi. So simply, once you reach this step, we're gonna do the reciprocal. The reciprocal, yani 1 over Xi on both sides. So here we will get Xi equal 0.51 meters, which is the same as 51.15 centimeters. So far, so good. So this one is the most dangerous step. You know, sometimes some students may get confused in this one and they may think that 1.955 is the final answer. Don't forget to do reciprocal. So the image now, it's positive. Since it's positive 51.15 centimeters, in this case the image is set to be a real image. The image is set to be real since Xi is positive. Of course, since it's real, it means, of course, from the type, we know what, also the direction. We know the direction. Real is the type, so the direction will be, in this case, inverted. So far, so good. Here, sample problem 2. Now, a candle is 49 centimeters in front of a convex spherical mirror. Be careful. Convex spherical mirror. Once you see convex, this word, keep in mind that F will be negative, even if it is positive 35 centimeters in the given. Even if it is positive in the given, so during calculations we're gonna put it in negative. What are the image distance and magnification? Is the image virtual or real? Is the image inverted or upright? And finally, draw a ray diagram to confirm your result. Solution. As usual, the given. A candle is 49 centimeters in front of the mirror. It means we are talking about what? We are talking about XO. XO is the distance between the object and the mirror. Now, F is negative 35 centimeters instead of positive 35. Be careful, since it's a convex mirror. the type of the mirror is convex, so f will be negative 35 centimeters. xi is unknown. We need to find xi. Now, in order to find xi, as usual, we're going to use this formula, 1 over f, the general formula, equal 1 over xo plus 1 over xi. By using the shift solve method, or by using this one here, by using the mathematical method, of course, 1 over xi equal 1 over f minus 1 over xo. So equals 1 over negative 35 centimeters. So it's not positive, it's negative 35 centimeters minus 1 over 49 centimeters. So it will be finally this one, negative 0.049, and don't forget to do the reciprocal. Don't forget to do the reciprocal. So finally, xi, after we did the reciprocal, xi will be negative 20.42 centimeters. So the image in this case is virtual, so it's behind the mirror, inside the mirror, since it's negative. Now, what if we want to find the magnification? As we said, everything depends on the given. We know that this is the formula of magnification. M equal hi over ho equal negative xi over xo. So we will take m equal negative xi over xo and not m equal hi over ho. To find the magnification, m equals negative xi over xo. So equals negative 20.42 over 49. It will be 0.42. Negative and negative, be careful, negative times negative, it will be positive. So the magnification now is positive. Once we know the magnification in this case is positive, so of course the type of the image is virtual image. The image will be upright, and in this case the image is reduced. Why reduced? The image is reduced since it's less than 1. 0.42 is smaller than 1, so the image in this case will be reduced. So far so good. Now, this is the figure here. The last part, they asked us to draw the figure. Here we have the object, since it's a B, since it is an convex mirror, so only one case, parallel to the principal axis, and then since it's parallel to principal axis, so the light ray, it will continue, or the reflected ray will continue its path to point F, but the reflected ray cannot penetrate through the mirror. Of course, it will be reflected in this form, and its elongated part will pass through F. The second light ray, now it's going through point F. Now the second light ray is going toward point F, but the incident ray cannot penetrate inside the mirror to reach point F, so it will be reflected parallel to the principal axis, and the elongating this one parallel, and the elongated part of this reflected ray gonna meet the elongated part of the first reflected ray, which is this one. So finally here you have the point of intersection between these two, A prime and finally B prime. So far so good. Now here we have sample problem 3. A concave mirror has a radius of curvature of 20 centimeters. You place a 2 centimeters tall object 30 centimeters away from the mirror. Part A. What are the image height and position? So, what are the image height or position? Part B. Find the magnification of the image. So, guys, try to solve this question by your own selves first, and then continue this video recording. Simply put pause, try to solve it by your own selves, and then continue watching this video. So far so good. So now in part A, what are the image height? So he's asking about HI, and what finally position. So far so good. We're gonna move on to part B. And be careful, the position. Part B, here you have the magnification of the image. Now the solution. First of all, part A, in order to find, first of all, the position, which is xi, we need to find what? F. Here the given was what? The given was the radius of curvature, which is this one, 20 centimeters. And this one stands for R. Not, it's this one, it's not F, it's R, the radius R. And in order to deduce F from the radius, simply we're gonna use this simple formula here, F equal R over 2, and equal 20 over 2, which is equal to 10 centimeters. Here we have given HO and XO. HO is 2 centimeters, XO here, XO is 30 centimeters. The same formula, the general formula now, 1 over F equal 1 over XO plus 1 over XI. In order to find XI now implies that 1 over XI equals 1 over F minus 1 over XO. The step equals, substitute, replace F with 10 and replace X with 30. So we will get 1 over 10 equal minus 1 over 30 equals 0.066. Implies that xi in this case it will be 15 centimeters. Again, don't forget to do the reciprocal. And the last step. Finally, we'll get 1 over 0.066, of course, which is what? The reciprocal, which is this one, 1 over 0.066. Finally, we'll get xi equal 15 centimeters. Now, this is xi. In order to find hi, keep in mind this relation always. M equals hi over ho equals negative xi over xo. Keep in mind this relation. Since now hi is given, or sorry, we need to find hi. We have ho given, xi we already found it, xo is given, so simply we're gonna find hi. Put the relation here, hi over ho equal negative xi over xo. Hi is the unknown, x. We don't know it, we need to find it. So hi divided by 2, substitute ho equal negative 15 over 30. So implies that hi equals negative 1 centimeter. In this case, we can deduce that since it's negative, so the height now, or the image, is inverted. So the image is what is inverted in this case. Now, hi in this case is less than 0. And the absolute value of hi, if you want to compare it with ho, also is less than ho. That's how you can deduce that the image now is what? Reduced and not enlarged. So this is how we can find xi and xo. Part B, we need to find the magnification. In order to find the magnification, so this is the relation. Here we have the relation. Now hi given, ho given, xi given, and xo is also given. So we can use the first one, which is m equal hi over ho, or we can use m equal negative xi over xo. It doesn't matter. Choose whatever you want. But I prefer to choose now, in this case, this one, because the values are smaller. The values are smaller, so it will be better. M equal hi over ho, and equal negative 1 over 2. So finally, the magnification is negative 0.5, and its unit less. So far so good. Now, the magnification here is negative, this means that the image will be what? The image in this case. So since magnification is negative, so m is less than 0, implies that in this case the image will be real and inverted. So to be real and inverted. So far, so good. And 0.5 here, it's what is less than 1. Since it's less than 1, so also we can deduce that the image will be reduced. So this is the last, this one was the last question. Simply, later on, there will be schedule about questions about this lesson, inshallah. Hope you enjoyed this video. Inshallah, we're gonna see you in another lesson.